Consider the angle I have shown here. The initial ray points in the 3 o'clock direction, and I've got the angle marked out here with this green arrow. And the measure of this angle in radians is shown up here in green. Now the slope of the terminal ray I have shown here in red. So right now this angle has a measure of about 0.9 radians, and the slope of the terminal ray is about 1.26. Now what we're going to do is think about how this slope, m, varies as theta varies over various intervals. And then on the right hand side, I have the graph of m in terms of theta. So on the horizontal axis, I'm representing the angle measure in radians. And then on the vertical axis, I'm representing the slope of this terminal ray. And as I move this terminal point around the circle, those two values are going to update. And then we're going to track this using a point and then trace that point out to draw a graph. So when theta equals 0, the terminal point lies at the 3 o'clock position, and that terminal ray has a slope of 0. So now I have a small angle and a very, very small slope. So near theta equals 0, we don't expect to have a slope greater than 0. And then, as theta increases, the slope of that terminal ray, you should see that slope increasing, and up here in red, we see this slope increasing. So as theta increases towards pi over 2, the slope of this terminal ray starts getting larger and larger. Now, as theta gets really, really close to pi over 2, the slope of that terminal ray gets increasingly large. We can make that slope as large as we want just by getting theta closer and closer to pi over 2. So on the graph over here, we see that from theta equals 0 to pi over 2, the output increases and then increases without bound as theta approaches pi over 2 from values less than pi over 2. Now, once this terminal point hops over the 12 o'clock position, we see the graph automatically jump down to a negative output. That's because the slope of this terminal ray is now negative. And we can make that slope as negative as we want just by making theta as close as possible to pi over 2. But then as theta continues to increase, that slope is still negative, but it becomes a smaller negative number, meaning it starts to increase towards 0. So as theta gets very close to pi, that terminal ray gets a slope that gets increasingly close to 0. So in our graph, we have a negative output over this interval from pi over 2 to pi, but the function output, which is the slope, is increasing up towards 0. Then from pi, theta equals pi to 3 pi over 2, that slope is again positive and increasing as theta increases. So as theta gets closer and closer to 3 pi over 2, the slope of that terminal ray becomes increasingly large. So as theta approaches 3 pi over 2 from the left-hand side, or from values less than 3 pi over 2, the slope of that terminal ray increases without bound. And we see that my computer can't even handle this. It just goes infinitely far up there. And then when we hop over that 6 o'clock position, our slope becomes negative, so we have an abrupt jump. And then as theta increases towards 2 pi, the slope of that terminal ray is still negative, but becomes closer and closer to 0. So the end result of this is a graph that looks something like this, where we have vertical asymptotes at pi over 2 and 3 pi over 2. And those correspond to the 12 o'clock and 6 o'clock positions, where our slope becomes increasingly large around those values. So this is what the tangent graph looks like, or the graph of the tangent function. Although this is just restricted from 0 to 2 pi, and this behavior repeats over and over again as theta increases, and this terminal point makes more and more trips around that circle. So this is just a piece of the tangent graph, but the rest of the graph just looks the same over intervals of 2 pi.